Namaste dosto. Today, we're stepping into the fascinating world of trigonometry, starting right at the foundation, the right angle, triangle, and how we define angles within it. Imagine you have a triangle where one angle is exactly 90 degrees. Yes, a perfect right angle. This special triangle helps us define what we call trigonometric ratios. Now, picture triangle ABC, where the right angle is at B. If we focus on angle A and call it theta, then the side opposite this angle is BC, the side adjacent to angle A is AB, and the longest side, the hypotenuse, is AC. Remember, theta is always one of the two non-right angles, usually A or C. This is important because our ratio definitions rely on that. Why do we do this? Because these definitions let us express the relationships between sides purely as ratios that depend only on theta, the angle itself, and not on the overall size of the triangle. It's like having a secret code embedded in the triangle, waiting to be unlocked. Areva, isn't that neat? Let's keep this picture in mind as we move forward. Continuing from our triangle ABC with angle theta, let's dive into the stars of today's show: sine, cosine, and tangent. Here's how we define them. Sine of theta is opposite over hypotenuse, that is, side BC divided by AC. Cosine of theta is adjacent over hypotenuse, so AB over AC. And tangent of theta? It's opposite over adjacent, BC divided by AB. So, sine and cosine compare a side to the hypotenuse, the longest side, while tangent compares the side opposite to the side adjacent, sort of like comparing the perpendicular height to the base. But a quick warning, these ratios only make sense when their denominators aren't zero. For example, tangent is undefined if the adjacent side length is 0, because division by 0 is a no-go. Here's the cool part. No matter how big or small you make your triangle, as long as the angle theta stays the same, these ratios remain constant. So, these trigonometric ratios depend solely on the angle theta, not on the triangle's actual size. Shabash, that's a powerful idea. You might have already noticed there's more to trigonometry than just sine, cosine, and tangent. Meet their reciprocals: cosecant, secant, and cotangent. Cosecant of theta is the reciprocal of sine, which means 1 over sine theta. Mathematically, that's hypotenuse over opposite side, AC divided by BC. Secant of theta is 1 over cosine theta, or hypotenuse over adjacent. And cotangent? 1 over tangent theta. The flip of opposite over adjacent becomes adjacent over opposite. These reciprocal ratios come up naturally when simplifying trigonometric expressions and solving equations. But remember, the same rules apply. To avoid any undefined situations, make sure we are not dividing by 0. For instance, you can't have cosecant theta if sine theta equals 0. If you imagine these on your right triangle, they each highlight different geometric relationships, painting a complete picture of side lengths around angle theta. Here's where the magic of algebra blends beautifully with geometry. Let's start with what we already know. Sine theta is opposite over hypotenuse, and cosine theta is adjacent over hypotenuse. Now, what happens if we divide sine theta by cosine theta? Written out, that's sine theta divided by cosine theta equals opposite over hypotenuse divided by adjacent over hypotenuse. When we divide these two fractions, the hypotenuse cancels out, leaving us with opposite over adjacent. This means tangent theta equals sine theta divided by cosine theta. Neat, isn't it? This equation links the three primary trigonometric ratios through straightforward algebraic steps, showing that tangent is not just another separate ratio. It comes directly from sine and cosine. Try repeating that slowly. Tangent theta equals sine theta divided by cosine theta. Keep this handy. This identity proves very useful in many problems ahead. Now, let's understand why these trigonometric ratios depend only on angle theta and not on the specific triangle size. The secret lies in similar triangles. Imagine two right-angled triangles that both have the same acute angle theta. Because of the angle-angle-angle similarity criterion, Their shapes are identical, though sizes might differ. This similarity tells us that the ratios of corresponding sides remain constant. So, the ratio of opposite side over hypotenuse in one triangle is the same as in the other, which means sine theta is constant. Similarly, adjacent over hypotenuse equals cosine theta, also constant. This shows that trigonometric ratios are functions of angles, not the length of sides. The size can change, but the ratios stay fixed. This is why trigonometry is so powerful. It gives us pure angle-based relationships. Isn't that wonderful? The geometry justifies all our earlier definitions with solid reasoning. Let's do a quick example to see these ratios in action. Given triangle ABC, right-angled at B, where side AB is 3 cm and side BC is 4 cm, we first need to find hypotenuse AC using the Pythagoras theorem. AC equals square root of AB squared plus BC squared. That's square root of 3 squared plus 4 squared. Calculating, 3 squared is 9, 4 squared is 16, so 9 plus 16 is 25. Square root of 25 equals 5 centimeters. So, AC is 5 centimeters long. Now, the ratios, sine of angle A is opposite over hypotenuse, so BC over AC, which is 4 over 5. Cosine A is adjacent over hypotenuse, AB over AC, which is 3 over 5. Tangent A is opposite over adjacent, BC over AB, that is 4 over 3. Using actual lengths gives a clear and practical way to calculate these ratios. Arey wah, concrete numbers make everything crystal clear. Time to meet some superstar angels. 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. These standard angles come from special triangles with neat geometric properties. For example, 30 degrees and 60 degrees come from splitting an equilateral triangle, while 45 degrees appears in an isosceles right-angled triangle. These give us memorable, exact values for sine, cosine, and tangent. Some values to remember. Sine 30 degrees equals 1/2, cosine 45 degrees equals 1 over square root of 2, and tangent 60 degrees equals square root of 3. These are fantastic shortcuts for exams or quick calculations. But be cautious. Some ratios are undefined at certain angles because their denominators become 0. For example, tangent 90 degrees and secant 90 degrees shoot off towards infinity, showing that division by 0 isn't allowed. Keep these values in your pocket. They're exam gold. Have you ever thought about how angles relate when they add up to 90 degrees? That's where complementary angles come in, and trigonometric ratios share beautiful relationships here. Key identities tell us that sine of 90 degrees minus theta equals cosine theta. Similarly, tangent of 90 degrees minus theta equals cotangent theta. Why does this happen? Because when you look at the other acute angle in our right triangle, the rows of opposite and adjacent sides swap. This neat trick simplifies many calculations and helps us reduce complex expressions involving complementary angles. And guess what? Each of the 6 trigonometric ratios has its complementary counterpart following this pattern. Isn't this like a secret handshake between angels? To wrap up, let's review the key formulas and ideas we encountered today. First, sine theta equals opposite side over hypotenuse. Cosine theta equals adjacent side over hypotenuse. Second, tangent theta equals opposite side over adjacent side, which is also sine theta divided by cosine theta. Third, the reciprocal identities. Cotangent theta is 1 over tangent theta. Cosecant theta is 1 over sine theta. And secant theta is 1 over cosine theta. Remember, these ratios only apply to right-angled triangles, and their values depend solely on the angle, not the triangle size. Using complementary angle identities can give you shortcuts in solving problems. However, be careful of some ratios becoming undefined at specific angles due to division by 0. Shabash! You've made great progress today understanding these ratios, the building blocks of trigonometry. That's all for today's session on trigonometric ratios. Keep practicing these concepts with different triangles and angles. Next time, We'll explore how these ratios help solve real-world problems. Till then, keep smiling and keep calculating.